For the next set of polar graphs, polar equations that we want to graph, these are what we call rose graphs. They all take on a very specific form. So you're either going to see a form that is r is equal to a times the cosine of n times theta, or r is equal to a times the sine of n times theta. All right, so basically what you're going to have is you're going to have a bunch of these loops that are all going to be connected. They're all going to be intersecting at your origin right there. The number of petals that we have is going to be determined by what n is. So if n is odd, then we have n petals. However, if n is even, then we're going to have 2n petals. Now, this is all provided that, a is not going to equal 0, because if a is 0, you just have r equals 0, and that's just kind of boring. N is going to be an integer. It's not going to be, it's not going to be equal to 0, and it's not going to be equal to 1. Because if you just have, cosine of theta or sine of theta, then you don't have a rose. You don't have a flower. You just have a circle, which is kind of boring compared to what we're going to see here. So let's look at the first example that we have. So r is going to equal 3 times the cosine of 5 theta. Now, here's what I do to help me out. Remember that cosine, and both cosine and sine, they have a maximum value of 1 and a minimum value of -1, which means for this graph, the largest possible r that I can have is going to be 3 or -3. So what I like to do, I like to go ahead and kind of dash that out and say, all right, I know that for my graph, I will not exceed this whatsoever. This is the highest that it can possibly be. Now, since this is an odd number, that tells me that I'm going to have 5 petals. Well, here's a bit of a trick. Think about it as though you would have 10 petals. I know it says 5, but if you could divide this whole circle into 10 regions, okay, each one, of course, being 36 degrees wide, you're not going to have a petal in each of those regions. You're going to have a petal in every other region. Now, when it comes to cosine, because if you start with theta equals 0, cosine of 0 is 1, you would have a radius automatically over here at 3, at the maximum value. From here, we would then need to draw 5 petals. Now, it gets kind of weird in terms of how do I set that up. So think about it this way. I'm going to have 5 petals. They will all be evenly spaced out. So what I like to do is I just kind of imagine this. I need to take 360 degrees, and I need to divide this by 5. So when I do that division, I end up with 72 degrees. So that tells me that about every 72 degrees as I go around this circle, I'm going to have another tip to a petal. Now, 5 is not the easiest guy to work with, so we're going to have to kind of guesstimate for this. So think about this. Each division that we have amounts to 15 degrees, right? Because we have 2 divisions to get up to 30 degrees, 2 more to 60, so each one's going to be 15. So that means that 72 degrees is close to 75. So if I go over here and I go here, that's 75 degrees, so back it up a little bit, and that should be 72 degrees. So that's almost 5 sections as I go across. Let's do that again. So 1, 2, 3, 4, 5. Back it up a little bit more. 1, 2, 3, 4, 5. Back that up even more. So then we have 1, 2, 3, 4, 5. Back that up even more like that. And so that's going to be roughly where these guys are going to be. Now, again, you can kind of play around with the math here and say, oh, so this is 72 degrees, 144 degrees, plus another 72, so that's what, 216, plus another 72, 288. So this is 270, 285, so 288, that kind of makes sense. All right, now if we're actually drawing this, again, this one's not going to be the easiest one that we do, but you know what? We can do it. So when you start graphing this, as you rotate about this, your radius is going to get shorter and shorter and shorter. So very quickly, it's going to come back here and it's going to cross, right? And where does it go from there? Well, it's going to go to this one, right? So it's helpful if you kind of number these. And again, it just kind of takes practice as you are working this out. So let this one be, try again. So if we let this one be the first one, he's going to circle back around, he's going to curve back around and hit this one next. And this one's going to curve back through and hit this one. And then that one's going to curve back and hit this one. And then finally it's going to hit this one. It's very similar to if you've ever had to change a tire and putting the lug nuts on, you kind of go crossways. You don't go in order, right? So you go here, you go over here, and you don't want to do the ones that are ever adjacent, right? So that's how we're going to build this graph. So, excuse me, I'm going to turn my drawing tablet so I can get the curves going nicely here. So a little pedal, you got to make sure that you cross through this origin. I'm going to hit this guy, and then I'm going to curve this back up here to my third little endpoint. And then I'm going to curve back around to get this one. And then I'm going to curl this. Got to turn it again. Sorry, excuse me. To hit this. And then we finally finish it off going through the origin again back to where we started. So it is a rose with 5 petals. Granted, this is not the prettiest thing that we've ever seen, right? But hopefully you get the idea about how we're supposed to build this and put it together. I don't know about you, but this kind of reminds me of a sand dollar. I was about to say starfish, but that's not what I mean. A sand dollar, you know, it's like a circle, and it's got those little 5 marks on it, kind of evenly spaced out. All right, so let's check with a graphing calculator. Let's see how we did here. So we have r equals 3 cosine of 5 theta. All right, so see, this looks kind of jagged. Let's go to the window and let's fix this. So the theta step, let's do this as pi divided by, let's say 360. All right, now it went kind of fast, but you saw that it kind of graphed it out the same way that we were expecting it to graph out. So let me change the step. Let's make it 720. Now let's see, because I know I'm using the computer and it's going kind of fast. Your calculator is not going to graph it this fast, but hopefully you can see how it's being built, right? It drew it the exact same way that we drew it, right? Now, watch what happens if I were to change this from cosine to sine, right? So you see how my cosine has the symmetry about the x-axis? Well, let's see about the sine. Now it has symmetry about the y-axis. All right. And again, this is where I like to just throw in different numbers and see what happens. If I were to change this from 3 to 5, it just makes it bigger, right? So it takes this little circle that I have here in red and just expands it out. All the other points would just be scaled out to make it bigger. That's it. No big deal. All right, so let's look at the next one that we have. So for the next one, we're looking at r is equal to 4 times the sine of 2 theta. Well, first off, I'm going to look at that 4 and say, okay, that's the largest that my graph is going to be. So I know that the tips of my petals will never be beyond this, because the max that sine can be is +1, the lowest it can be is -1. All right. Now, because we have a 2 right here, and it's even, that means that we're going to have 4 petals. So if n is even, you double that number, and that's how many petals you're going to have. All right, so let's see and think about how this is going to be built. For all of the cosine ones that are flowers, you're going to be starting here at the max value. But sine is different, right? Because if I start here at theta equals 0, sine of 0 is 0. So he's starting right there. Where do I go? Well, what if I try to do... Let's do this, because maybe it's easier this way. If I try to plug in, say, pi over 6 or pi over 4, what happens here? Well, if I do pi over 6 into this, that gives me 2 pi over 3. No, sorry. It gives me pi over 3. So then we would have pi over 3, sine is square root of 3 over 2. So we'd end up with 2 square roots of 3. Not very helpful, right? What about pi over 4? 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. So that would give me 4. I think that's going to be the one that breaks it open for us. So it says that pi over 4, so angle it out this way, this is where we're going to reach our maximum value. So we're going to go from here to there, and that's going to be the max. I'm actually going to throw one on here. It's really not in order, but if I do pi over 12. Because if I do 2 times pi over 12, I get pi over 6. And sine of pi over 6 is 1/2. And so we would have 2. You might say, well, there's no pi over 12 on here. Yeah, we do. Here's pi over 6, so pi over 12 is going to be this little guy right here. So we would have that. Now, the more you mess with this, the more you're going to see that there is going to be some symmetry. And it's going to be symmetry about, well, there's going to be a ton of symmetry here. But first and foremost, we have symmetry about the pole. I think we did an example of that earlier. If I were to do, I think, not that, come on now. If I did 5 pi over 12, so angling out this way, 5 pi over 12 times 2 is 5 pi over 6. You still get 1/2, and 1/2 times 4 is 2. So right here, we're out at 2. So I hope that you can see that in this one part, our petal forms like this. We've got to curve out, hit that, and then come back in. And you're going to start to see the pattern that forms here. We have 4 petals, and so if you were to take this grid that we have right here, and you were to divide this into 4 equal quadrants, because we actually do have quadrants here, right? You're going to find that you have 1 petal for each of these quadrants. So that's the thing. When we had, in the previous example, we just had 5, right? So you could divide this into 10 sections, and what we don't have here is that we don't have a petal here, here, and so on. It's almost as like they could have been there, but they're just not. So if you divided this into 10 equal regions, every other one would have a petal. But when it's an even number inside the 2, divide it into the 4 regions for the 4 petals. Each region will have a petal. So if I were to start to draw this, it starts here and it curves out, and it's going to curve back in. Now when it comes down right here, I hope that you can see there's only one place for it to go to keep that motion smooth, and that's going to be to curve back over here. Now, we had a maximum value at pi over 4, and so all these pi over 4 type places is where you're going to have a max value. So he's going to have a max value in this one, at this 5 pi over 4, and at 3 pi over 4. And the way that he's going to progress through these is that this is the first one, he's going to curve over here and hit the second one, then he's going to curve and hit the third one before curving back out and hitting the fourth one. So here we go. We're going to curve. And when he comes back through the origin, he's still curving in that same general direction. He makes his turn, come back through the origin, and still make this turn. And so it should look something kind of like that. Now, I admit that my first pedal may not be as good as it should be, but again, this is a general idea for what you would have. And let's check with the graph. So we've got 4 sine of 2 theta and graph. And so you can see it graphed it in the same order that I graphed it in. Now, notice the subtle difference if I were to do cosine. So I'm going to actually keep the sine there. I'm going to do 4 cosine of 2 theta. And let's see what happens with that one. Ooh, how pretty is that? You see there that cosine starts off being the max along the polar axis. And the way that it's going to graph it is it starts here, it curves out, and then it has that same kind of curling pattern that we had with the sine. It just starts at a different point. Now, of course, knowing me, I'm the kind of person who says, oh, you know what? Let me just draw, a 4 there, and let me draw, a 2. Let's, just have pretty graphs, right? A bunch of circles, a bunch of rows. It makes me feel good. Doesn't that make you happy? If not, what's wrong with you? All right, so we got a couple more to do, so stick around.